Yeah, he's recording. Continue. Okay.
Okay.
Okay. So I'll now start my second lecture. So hope everybody can hear me. And I displaced this view graph from yesterday's talk for a reason. That yesterday there is one thing we discussed in yesterday's lecture: recombination of permeable plasma and thermal history in the post-recombination era. And it was a story of two kinds of decouplings. One was thermal decoupling, which I showed, but I didn't quite mention the other decoupling that happens close to a redshift of 1000. That is the decoupling which is of even greater importance to us, and we have a lot of proof of that. Is that photon after from this roughly around this era, and you can see it's a continuous curve. I can't put a number to it. Photon doesn't scatter again. From this epoch, the ionization fraction falls to such a small value that a photon can only interact with the ionized plasma, and the fraction of electrons in the plasma is so small that photon really free streams from epoch of recombination, which is roughly a redshift of 1000. We put a redshift of 1000 to that. I could have shown you the visibility, which would show you more clearly, but this would suffice for the moment. So most of those photons that we see, CMB photons, actually are coming from that era. The era of reionization, which I haven't shown here, it causes rescattering of around 7-8% of those photons, but most of them are from this era. So this is also called the era of epoch of decoupling. It is decoupling of a different kind. Photons from this era come straight to us without getting scattered again, except 7-8% that get scattered during the epoch of reionization. And one very important thing, which I should just mention it because I do not have time to cover, is that of this era, roughly around redshift of 1000, we have fantastic amount of information. The best information in cosmology comes to us from this era, from CMB anisotropy. So this ionization recombination history, you might have thought I have produced this theoretical curve, but this theoretical curve is incredibly well tested. Up to the point that the ionization fraction is around 10% or so, which is roughly here, you can see, ratio to 1000. After that, it's difficult to, because very few photons actually get scattered again and again. After the, after the ionization fraction falls below, 0.1 or between 0.1 and 0.01. So after that, we do not know much. So most of this curve that is what is called dark ages, it lies between two epochs. One epoch where CMB anisotropies form, which is around redshift of 1000, and another epoch, which is to the left of this curve, beyond redshift of 10, which is the epoch of reionization. We are somewhere in the middle, and it's very difficult during this era to say which of this ionization history was actually correct. So having said that, I will now move on to the topic of discussion today. So today is more like a lesson in thermodynamical equilibrium, and I will talk about how the level population of neutral hydrogen, the hyperfine levels, is determined. You have, I'm sure, heard about hyperfine level, but I'll spend some time, especially the numbers that I want to talk about I have listed here. So a bit of it would be what you have already heard. So hydrogen ground state is a 1s state that we know. It splits into 4 hyperfine levels because of the coupling between the spin of protons and electrons. This happens when spins are alone, and for instance, it happens for hydrogen. It doesn't happen for helium. It doesn't happen for helium-4 at all, because there's a neutron there, and there are protons and neutrons, and they cancel each other's spin. So there is no such coupling. Hyperfine coupling doesn't happen for neutral helium. It does happen for one species of helium, which is He3, where you have 2 protons and 1 neutron. So there is a spin imbalance there. And when you ionize it one time, it creates a hyperfine split, but I'm not going to talk about that during this talk. So our focus would be the ground state of hydrogen, which is 1s, and 1s splits into 4 hyperfine level, owing to the coupling of proton spin with electron spin. It can be shown that the upper level is triply degenerate. It has a degeneracy of 3. And the lower level is a singlet. It has a degeneracy of 1. The energy difference between the two levels, you have heard plenty of times during these lectures, corresponds to a frequency of either 40-20 megahertz, or more famously, this line is called 21 centimeter line, which corresponds roughly to the wavelength of this transition. What is of interest to us for this lecture is that I can find an equivalent temperature for the line, which is H nu12 divided by K, where K is the Boltzmann constant. K, I will, throughout this lecture, K is in Boltzmann constant. And you see, this is a very small number. It is 0.068 Kelvin. So it is the temperature corresponding to this line is extremely small. It also means that the energy is so small between the ground to the ground state, the split of this ground state between hyperfine levels, it's very, very easy to excite it. So excitation means that I want to put something from the ground state to the upper state of the hyperfine levels. If it costs only so much of energy, 0.068 Kelvin, it is incredibly easy to excite it. Energetics is not a problem. For comparison, I mean, I've just written for comparison because we're going to use it. If you were to compute the equivalent temperature for the Lyman alpha line, it is 10 power 5 Kelvin. So if a medium is roughly at such temperatures, we are able to excite Lyman alpha lines. But very, very cool medium can still excite the hyperfine line. And this is, in reality, the principal reason. Our best way of studying hydrogen is a hyperfine line in emission. All the relevant information that we have ever got in the last 50 years of hydrogen in emission has come from hyperfine line. While if you want to get information about hydrogen in absorption, most of the useful information has come from the Lyman alpha transition. And the reason is you need a pretty hot medium to excite the Lyman alpha line. And by the time the medium gets this hot, it starts ionizing. The medium is no longer neutral. And that is why Lyman alpha line in emission is nearly impossible to see, while H1 is harder to see in absorption. It is very easy to see in emission. So that is the importance of hyperfine line for astronomy. And that is why our focus is also on this line. Even though you will realize overall, you will realize it's incredibly weak line, and that is the next part. The decay rate of this line is 2.85 into 10 power minus 15 per second, which basically means if you put all those atoms in the excited state of the hyperfine structure, it'll take close to 1 million years for one of the atoms to decay. 1 million years. That's a very long time, actually. This is one of the slowest you can actually find. In all of quantum processes, you have really not come across any quantum process so far, none that I remember from my undergrad classes or later on, which has a coefficient as small as this. And again, this should be compared to the decay rate of the Lyman alpha line, which is 6.5 into 10 power 8 per second. It's 23 orders of magnitude difference between them. So if you put 10 to the power 8 atoms in the excited state of Lyman alpha, they will all decay in a second. They will all have decayed. But if you put one in the hyperfine line, it'll take almost 1 million years for it to decay. It's an incredibly slow process. And historically, and I'll tell you a bit about history, this line was first seen in interstellar medium for that reason, the hyperfine line. It was very difficult to see this line in the lab because its decay rate is so small. It easily gets de-excited by other things, collisions. But by 1960s, it had been seen in cavities. And that confirmed what people had already seen in interstellar medium, that such a line exists. And indeed, it has a decay rate, which is very small. But again, let me say it again, why we are studying a line which is as weak as this? It is because this is our only hope of detecting neutral hydrogen in emission. We cannot detect neutral hydrogen in emission by pretty much anything else, and the reason is given just above. Our only other hope would be a Lyman alpha line, which does not occur, which actually it's a very strong line from recombination region, which are fully ionized. But it's no probe, it's a good probe Lyman alpha line, actually less Lyman alpha because it doesn't escape H alpha from 3 to 2 of ionized regions, but not of neutral regions. You want to study neutral, mostly neutral regions in our galaxy or in the universe, you have to rely on this very weak line. For the rest of my talk, I'll talk about how the level population between the hyperfine structure is determined. What causes the excitation and de-excitation of hyperpine levels. And I'll talk about multiple processes here. CMB is always there. So let's see, just imagine you have a parcel of gas, almost completely neutral, put it at redshift of 500. It's up to you. You already know that the gas is mostly neutral after redshift of roughly 900, right? The ionization level has fallen to below 1 part in 10 power 2. So gas is mostly neutral. So in this neutral gas, there is always something from behind it. From as far as we are concerned, when we see this part of the neutral gas, there is something coming from behind, and that is CMB. So we first want to know, what role does CMB play in the excitation and de-excitation of these lines? So first thing that has to be, of course, taken into account is that if you leave the atom, it will decay from the upper state to the lower state. This is a process which is always ongoing, right? Upper state does decay and the lower state is stable. But you can see that this rate is 1 part in 10 power minus 15. I mean, we already discussed it in the last few graph, which means it's a very, very slow process. And this turns out to be the slowest process of all of them, and doesn't play actually a role in determining the level population. I'll retain it for the rest of the discussion, but neglect it at a later stage. So you leave a hydrogen atom at a redshift of 500. What processes are determining its relative population of the two levels? Spontaneous decay, yes, but A to 1 is even smaller than the expansion rate. So it's a very slow process. What else? Well, it interacts with CMB. The CMB is a black body, and it has a temperature of TCMB, which at a redshift of 100 currently is 2.73, and it increases as 1 plus Z. It's around a redshift of 100, it's around 273 Kelvin, right? It's a room temperature actually. I mean, around us, I mean, not room temperature. Room temperature is close to 300, but yeah, close to 0 degrees Celsius. That's the temperature of CMB at a redshift of 100. What does it do? So first thing that I would do is, I'll not write down the more complicated formula of the specific intensity of CMB with all those exponentials of h nu by kT in the denominator. And I will simply first find the form which corresponds to h nu 12 much less than TCMB, which is always true here, and you can actually compute. H nu 12, the equivalent temperature of this line, you remember, was 0.068. Let's say 0.07 Kelvin, which is tiny compared to TCMB at all redshifts of interest. It's even smaller than CMB temperature at the current epoch. So that's a good assumption. In that case, you can write down CMB specific intensity in a much simpler form, 2K TCMB divided by the wavelength of the line square. And that I leave it to prove. It's a fairly simple proof, and you have done it plenty of times in your undergrad days. Okay. So this intensity is falling on this level, this hyperfine structure. There is a rate at which the upward transition takes place. You call it absorption. And that rate is computed easily in terms of what are called Einstein B coefficients. So that is, take the intensity of CMB multiplied by the B12 coefficient, and B12 coefficient can be written in terms of, yet again, the decay of the line and the frequency of the line. And I've written the explicit form here, and you can readily verify it. Similarly, there is a rate of downward transition. This is called stimulated emission. And the rate of this process, again, can be written very simply. It is the intensity of CMB multiplied by the Einstein B coefficient 2,1. And of course, B12 and B21 are related. One of them is 3 times the other, because 3 times, there are 3 times as many atoms. The digit ratio of the upper state is 3. So now you can see these two processes, along with the spontaneous decay, determine the level population of the the hyperfine structure. So if you were to calculate the level population in equilibrium, now that's the most important thing, and I'm going to use that notion again and again. In equilibrium, these two processes will be equal to each other. And if you remember, when you were introduced to Einstein A and B coefficient in your undergrad days, you have seen equation 8. So if you remember, Einstein A and B coefficients were introduced by the following notion, and I want to emphasize it actually because it's important, that you have a radiation field which is interacting with the two-level system. You never say what the two-level system is. You simply say it's a two-level system. That's a hypothetical experiment Einstein had in his mind when he wrote this paper on Einstein A and B coefficient. His hypothesis was the following. You have a two-level system which is interacting with the radiation field. And we believe that the level population has relaxed to equilibrium. Level population relaxes to equilibrium when the rate of upward transition equals the rate of downward transition. That's exactly what has been assumed in equation 8. If that is the case, and that was a point Einstein made, and we'll use it again and again during this lecture, then the radiation field that is interacting with these atoms, this two-level system, must be a black body. That is the only way you can have equilibrium. Otherwise, the system is always out of equilibrium, so it will evolve. So equation 8 will not be strictly valid. And by writing this, he derived the intensity of the radiation field using the fact that N2 by N1 will relax to a Boltzmann form, which we knew from statistical physics at that time. And he derived the black body form, and thereby, and that is when he actually stipulated that we need to have a process called stimulated emission. Otherwise, we will never attain thermodynamical equilibrium. So to attain thermodynamical equilibrium, stimulated emission is needed. And that's a very, very important result, right? You always wonder why stimulated emission is there. It's there because we need to, if we are going to study two processes in equilibrium, a two-level system with a background light, then we need to, without stimulated emission, there is no equilibrium. So equation 8 is something you have seen before. We are using it in the reverse form. We are already given a black body, and we are interested in computing the level population. In equilibrium, that level population would be given by the Boltzmann law. Okay, so this is one. I can compute N2 by N1 from this equation, and I know the form it will take because it's already interacting with the black body. Process 1. What are the other processes? Well, you have atoms and you have electrons and protons in the medium. Electrons and protons are fewer in number, right? The fraction of electrons and protons, remember, we are almost neutral. We are mostly in a neutral medium. So there is collision between hydrogen atoms and other particles, electrons, proton, other hydrogen atoms. They can exchange energy through collisions. So these processes can excite the hyperfine level and can de-excite the hyperfine level. These are all quantum processes, and there is a bit of physics here which is needed and which will probably start playing an important role in many studies which are going to be done in coming years. And that is the reason I actually included this particular view graph here. H-H collision is generally a weak process because both particles are neutral. So quantum mechanically, if you have two neutral particles which are coming towards each other, how do they interact with each other? Quantum mechanically, it is a fluctuating dipole of one which interacts with fluctuating dipole of the other. It's a 1 by R6 process actually, 1 to the power 1 by R6. It's a very weak process. For all intended purposes, the cross section of this process is actually close to the geometric cross section. So hydrogen atom can be viewed as it is something in its ground state and is a size of around an angstrom. You see, its ground state is around 0.5 angstrom actually. So it is processes, the cross section of this process close to the geometric cross section, which is the square of that number. I put in a number. I mean, it's factor of 3 or 4 around it. So it's a weak process, and the cross section can be computed from very general argument because it is very close to the geometric cross section. HP and HE collisions can have larger cross section and will. In fact, you may ask, how does a hydrogen atom interact with a charged particle? A charged particle induces a dipole in the atom, and that dipole actually interacts with the charged particle, and that is a 1 by R4 process actually. It's a stronger process. So these collisions also have cross sections which could be few orders of magnitude larger, and they are not really easy to compute. You might think they are very well understood. There are issues here, especially at very low temperatures. And the book of Drain on interstellar medium is probably a good place where you can look this up. And HP and HE collisions are completely different quantum processes because of the difference in their masses. And these processes have been studied, like from the first paper of field where they're given. These processes and their cross sections have changed. The issue is, and that's why I have put this view graph, in the post recombination gas, the ionization fraction is tiny. So even if these processes have larger cross section, the abundance of these electrons and protons is much smaller as compared to hydrogen. So HH collisions generally dominate. But will they always dominate in partially ionized gas, X-ray heated gas, where the ionized fraction is 1 by 10? Well, not really. Janki in her notes has given some numbers here of these processes. So I would like you to now go, I hope I have motivated you to look at those numbers. It may have some bearing on how we compute the evolution of some of the things of relevance to us. But my aim was not to lead you there, but just to give you a sense of what the important processes are. So for the rest of the lecture, I'm going to assume it is HH collision which is dominant, because the gas I'm going to assume is at a very small ionization fraction level, 1 part in 10 power 4. So what is the rate of downward transition here? One can ask. And yet again, we can find that rate. That rate is the number of hydrogen atoms. That rate would be, so again, let's pay attention to this. Number of hydrogen atoms, sigma, which is the cross section between these two collisions, and cross section, I said, typical cross section is around 10 power minus 16 centimeters square. V is the relative velocity between the two species, and relative velocity between the two species is generally, again, it's typically the thermal velocity, which is 2 kT by mp, square root of that. So this is a relative velocity, and you actually average over the thermal distribution. And that's how you get this. What I would like you to prove here, and this is something I mentioned yesterday also, that all components share a common temperature, which is what I call matter temperature in yesterday's class also. So you see, in the post-recombination universe, what kind of a system do we have? We have electrons, we have protons, we have neutral atoms. When one part shares energy with another, is it given to the other components or not? When I wrote down that equation yesterday about the thermal evolution of the post-recombination plasma, I wrote down a single temperature and called it Tm, which is what I called matter temperature. You may recall it. This was called matter temperature. And at that point, I asked you to show for yourself that all the other components share this temperature. I would like, actually at this point, I'd like to stop and ask you if you understand what I'm trying to say here. So I'll stop and I'll take a question on just this issue if you have any further questions. This is important. I encourage you to ask questions when I'm speaking. So please go on.
You can unmute yourself and ask, please.
So I have a question related to this TM,
Go on.
the matter temperature. the question is, I mean, you mentioned that different species, for example, proton, electron, and neutron, they have a same temperature. Do you mean that the velocity distribution is same?
What does a common temperature mean?
The velocity distribution is same, but their masses are very different, right?
No, absolutely. I'm not saying the velocity distribution. Same
Okay,
temperature mean their average kinetic energy is the same.
correct. So that means the velocities would be same. The distribution of the
No,
velocity
velocity distribution will be different
different. Okay.
because you yourself said it, right? The masses are different.
Okay. So because of the mass, the velocity distributions would be different, but
So
the kinetic energy will be same.
yes, so the average, when you say something is in thermal equilibrium,
Mm-hmm.
right?
Mm-hmm.
That means they share the same temperature, right?
Correct. Correct.
So roughly half mv square is equal to kT for all species, right?
Right. Right. Correct. Correct. So m is different, so v is different. Yes.
That is correct. So
That's
velocity of proton and neutral atoms would be more or less the same because electron is like it doesn't have
correct.
mass, but electrons are moving much faster in this medium.
Mm-hmm. Correct.
See my point? Because they
Mm-hmm.
share the same kinetic energy. They have relaxed to thermal equilibrium.
Correct.
You can envisage in equilibrium another kind which doesn't actually happen very easily, where the
Right.
momentum is shared.
Mm-hmm.
Okay, that's
Uh,
where the kind of their velocities will be the same.
correct. But the number of electrons would be much less as in the post recombination era, right?
That is
Because it will
correct.
be just
That's correct.
residual electrons.
That is right. So
Mm-hmm.
whatever is the number of electron,
Mm-hmm.
right? The number of electrons, the ionized fraction is 1 part in 10 power 4, right?
Correct. Correct.
That means the number for each neutral atom, there is only 10 to the power minus 4 electrons
Correct.
and protons.
Mm-hmm.
Point I'm trying to make here, and this is a
Mm-hmm.
very important point, is that these components, when they collide with each other, the cross sections are still large enough, right?
Right.
That they relax to a common equilibrium.
Correct.
So I don't have to worry about, and which is an important problem, I don't have to worry about the evolution of their temperatures being different from each other.
Correct.
And the
No,
reason
and
has
the
to
other thing,
what?
at every redshift, do you get this kind of equilibrium that the temperature of all species is equal, or is there any redshift at which there will be some kind of
So you see,
uh-huh.
one has to work out the cross section.
Mm-hmm.
So I will give you typical numbers.
Mm-hmm.
Okay. So electron protons equilibrate. So there are, okay, what are the various processes between
Mm-hmm.
equilibrium between different? So you see momentum exchange and energy exchange are different things. So
Correct.
there is collision between electron proton and proton proton.
Mm-hmm.
If you heat electrons, they will share energy with fellow electrons on a time scale, which is, again, everything is Rutherford scattering, right?
Correct.
But that is the shortest time scale.
Mm-hmm.
Proton, that time scale is, so that time scale is seconds,
Correct.
actually. So that is much, much smaller than expansion rates.
Mm-hmm.
The
Correct.
proton, that rate is larger by mp by me square root. So it's
Right.
larger, but still much smaller than any expansion rate or any other scale in the problem.
Correct.
Electron proton is larger still by mp by me of electron, but still it is small enough. So
Correct.
as far as the charge component is concerned, the energy exchange is extremely quick.
Okay.
It's mediated by radiation, by Rutherford scattering, right?
Correct.
And that is because they are all non-relativistic. If they were relativistic,
Mm-hmm.
these cross sections dramatically reduce. Relativistic electrons do not interact with other electrons very easily. So suppose I were to put in a relativistic component in this,
Mm-hmm.
something people do study, like propagation of cosmic rays in the neutral medium. Okay,
Correct. Mm-hmm.
that interaction rate is much slower because
Right.
relativistic particles do not interact so readily with each other as non-relativistic particles.
So just after CMB as well, the particles are not relativistic just after CMB.
That you see, you have to compute again, then they are in thermal equilibrium.
Right.
The rest mass of electron
Mm-hmm.
is 0.5 million electron volt.
Correct.
And the temperature of the medium is around 0.2 electron volt. So
Right.
there is a
Right.
factor of million here.
Correct. Correct.
So if electrons are non-relativistic, of course, protons are non-relativistic too, because their
Of
mass
course.
is 931 million
Correct.
electron volt, right?
Right. Right.
The important process here is the balance between protons, electrons, and neutral atoms. How do they exchange energy?
Correct.
That is a slower process, and that is slower by many orders of magnitude. And that's why I raised this point. But it is still fast enough at all redshifts of interest to us in the post-recombination era to
Correct.
still maintain an equilibrium between these three species. So it is true that at all reaches of interest, these three species always remain in equilibrium with each other.
Correct.
One can compute. So what I'll do, I will put in some numbers. I mean, I have not put in numbers between electron neutral atoms interactions. Okay. But I'll ask probably Janki can do that. And you can play around with those numbers to show that it is indeed the case.
Yeah.
That
And in
all
the,
these components share a common temperature. Go on.
yeah. And in the previous slide that you mentioned that there could be collisions between proton and electron. Do you mean this is a recombination or is just a collision?
Protons and
Electron collision, proton and electron collision means recombination.
This is collision of proton and electron with neutral atoms.
Neutral atoms. Okay.
See, because it's a neutral atom which has a hyperfine structure, right?
Correct. Yes.
So again, I have written HP and HE collisions. Those are of interest to us.
Okay. Yeah. Thanks. Yeah.
Okay.
Yeah.
All right. So this will be shown to you, but you can actually study. In fact, sigma V for a proton neutral particle collision is around 10 power minus 9. If you can remember that number, right? If you can write it down, sigma V is on the order of 10 power minus 9. Right. So that is for charged particle, which is actually a proton and neutral particle interaction. If you can remember this number, you can compute whatever you want yourself, because you know the number density of particle, you know the velocity of the particle. Why? Because you know the temperature. So you can compute the velocity of the relevant particle, right? Compute it yourself and you'll find this is indeed the case. So they do not decouple from each other thermally, these three components. They remain always in equilibrium. And this temperature Tm is much, much larger than T star, which is, T star, remember, was the temperature of the hyperfine line, which is very tiny. Okay, so I think I can move on now. So we had a bit of discussion, and I encourage you to stop me anytime you wish. In statistical equilibrium, again, statistical equilibrium is important, which is governed by collisions. These two processes will equate with each other. The number of particles in the ground state and the number of particles in the excited state, they would be related in equilibrium like this. This is a very important relation actually, because this allows us to compute the rate of the inverse process in terms of the rate of the forward process. So whenever we study any of these processes in interstellar medium, what we compute is the rate of one process, which is the de-excitation, which is easier to compute. And after the rate of de-excitation is computed, we go and ask ourselves, what would be the what would happen in thermal equilibrium? In thermal equilibrium, N2 by N1 will relax to the Boltzmann form. That gives us the rate of the inverse process. By the way, if you notice the inverse rate, 0 to 1, has to have this exponential factor because energy needs to be conserved. Right? You are trying to excite something from a ground state to an excited state. You need to have enough energy to excite it. Right? So whenever we actually talk about excitation will always come with this thermal factor and exponentially suppressed factor because we need energy to cause that. Sorry, I've forgotten to put a P0, P10 here. So equation 11 is incorrect. P01 is G2 by G1 multiplied by P10 and exponential of h nu. So this is a mistake here. So it is related to the inverse process. You can see equation 10, if you solve after N2 by N1, that's what you would get. So what I'm trying to say here is that in thermal equilibrium, we can actually find the inverse rate. And once we have the inverse rate, we can compute now N1 and N2. You may ask, actually, you used N1 and N2 to compute a rate. Now what more is there to compute, right? And this is a question one should always ask, that you started with equilibrium, used a form of N2 by N1, and then you computed this inverse rate, then what remains? Now, why do you want to again compute N1 and N2? The reason that we can still do it is that so long as we are in near thermal equilibrium, but may still be out of equilibrium. The particles are in equilibrium, but the hyperfine levels could be out of equilibrium. This happens all the time actually. In that case, equation 10 may not give you solution N1 by N2 equal to G2 by G1. It might give you something else. But equation 11 would still be correct because quantum mechanical processes do not depend on whether you are in equilibrium or not. It's a subtle statement. I want to think about it and we can discuss it at some stage. Now I go on to the subtlest process of the lot. And I think I'll first show you the Lyman alpha cross section because it's important. So the third process that mixes the levels between hyperfine levels is Lyman alpha. First, maybe I'll show you this plot and then I'll come to the next one. So what is plotted here, you can see these are level populations. This is n1, n equal to 1. And the hyperfine split is shown at the bottom left. S half, upper state is 1. Its angular momentum is unity. The lower state has angular momentum 0. Both of them are S state with respect to the orbital angular momentum. But this is 1 with respect to the spin, and this is 0 with respect to the spin. On the right-hand side, you are shown the n equal to 2 state. This is not plotted on scale. This is actually from the original paper of field. And the n equal to 2 state has a 2s level, but you cannot have a photon transition from 1s to 2s because that's forbidden by angular momentum conservation. So you can have, but you can have transition to the 2p state. So these are all the splits of the 2p levels. While this is called the hyperfine level, the split of the ground state, this is called the fine structure. The split of the first excited state comes from fine structure. This is called hyperfine. This is called fine. Oh, this is a hyperline I have written actually. Hyperfine I should have written. So you can actually see that you can make a transition from either the ground state or the first excited state to different excited states. And there is a genuine probability. So let's take this line, solid line, which starts from the ground state 0s half, goes to 1p half and returns to 1s half. This can work both ways. So this can go up and come down. And what is listed here, 2 and 1, and this is actually discussed in Janki's notes, so you can see, these are probabilities of these transitions. So you can actually see that you can actually mix levels by these transitions. You can go from using an intermediate P level from the ground state of hyperfine level to the first excited state of hyperfine level, or vice versa. You have yet another route, which is going from 0s half to 1p3 by 2. That probability is 2. And then you can come back to 1s half, and that's probability of unity, or the inverse. Both of these processes are possible. So there are two routes listed here, the solid lines, which connect the ground and the excited state of the hyperfine level. There are other things which are actually forbidden. Actually, it's interesting that there is this dashed dotted curve, which is called complementary. You can go from the excited state up, come down, but you cannot come down to the ground state. You can come down to the same level, but make a transition to another level. From where also it's forbidden to go to the ground state. So for instance, a pair of dotted dashed line is what is called complementary. You always remain at the excited level. You never really mix. On the other hand, forbidden is dotted. You can go up, but you cannot come down that other route. So there are two possible routes. In fact, both possible routes are shown here, where you can actually either start from the excited state or from the ground state and go to the other one with a certain probability. So you can link, you can mix hyperfine levels through this process also using Lyman alpha. This has a name. This is called field. I mean, there is a Dutch name which I can never pronounce, right? So I'll call it field effect. And it was discussed in 1950s. And it's one of the most crucial processes for mixing hyperfine levels even in the interstellar medium. Even though in interstellar medium, like in the early universe, we do not have a good idea of the Lyman alpha intensity of Lyman alpha photons. Why Lyman alpha is so important, and this is what I wanted to show. I just wanted to show you one curve of Lyman alpha cross section. It's a very important curve actually, which has a bearing on many things, but I'm only going to use part of it. What I have plotted here on the y-axis is a cross-section of Lyman alpha. This is for a redshift of 1000. On the x-axis, what I have plotted, they are numbers -20, -100 to +100. They are in the units of the thermal width of the line. If you notice, you are very sharply peaked around delta nu d, very close to -1. The peak cross section is very large, it's 10 power minus 13. If you were to take an average across delta nu, it's still around 10 power minus 16. I did list that number yesterday in my notes. So this cross sections, the Lyman alpha transition. So once you have Lyman alpha in the medium, and that's what we discussed with respect to recombination also, it really mixes things well. And that's precisely what happens by these processes. Once you have Lyman alpha, these processes will take off. They will start mixing levels of the hyperfine line. So what would be the rate of this? Oh, everywhere in my new graphs, I have actually written hyperfine. I have written hyperline. You'll excuse me for that. I mean, this is correct. So Lyman alpha, or any transition from the ground state. So Lyman alpha, if Lyman alpha can do it, you may immediately ask, how about something else? Why not Lyman beta? Well, I suppose Lyman beta will do exactly what Lyman alpha does. It's not that it can't do it, except for the fact, and we discussed it yesterday, Lyman beta line will break into an H alpha line and a Lyman alpha line after a few scattering. So it doesn't really make a difference whether it's Lyman alpha or Lyman beta. We can keep discussing the transition between the lowest two states, n equal to 1 and n equal to 2. The rate of this transition is simpler. It is the number density of Lyman alpha photons in a small range of frequencies, which is around delta nu d from the last plot, so unity. So it's within the thermal width, close to the resonance. That's where most of the scattering occurs. Sigma alpha, I showed you sigma alpha in the last plot. So you can take the sigma alpha averaged over thermal width, multiplied by C, and the C you would expect actually, because the relative velocity between an electron and a photon is always C, right? It can, and that's what makes a huge difference. This rate generally has a rate, this process generally has a rate much larger than collisions, and I will show you those numbers. What is interesting again is that suppose I switch off the other processes, I switch off CMB for some reason, I switch off collisions. I can't, but suppose I do. And this was the only process that was responsible for mixing the level population. Then again, I will ask what happens in equilibrium. Now you see what I was talking about in the last view graph. I write down the equilibrium, but again, I have made a mistake here, which gives, I should have put a P10 alpha here in equation 13, which I have forgotten. But now this actually defines T alpha. I do not know what N2 by N1 is. I am going to express N2 by N1 as G2 by G1 exponential of minus H by KT alpha. T alpha may or may not be equal to any other thermal temperature. It is an abstract quantity that I have defined. But in thermal equilibrium, T alpha does become Tm, and I will not have time to talk about that. So for much of the rest of the discussion, I am not going to talk about the difference between T alpha and Tm. I will assume that T alpha and Tm are the same. And that requires a bit of calculation, somewhat difficult calculation to show that indeed in thermal equilibrium, after a fair number of scatterings have happened, this relaxation occurs. So again, to reiterate what we have achieved. So we achieved the level population, the hyperfine level population. They can either relax to CMB temperature, or they can relax through collision to matter temperature. Or through Lyman alpha, they can relax to yet another temperature, which I called T alpha, or in astronomy literature, this is called, it is light temperature. It has various names actually. I forgot, it's called the color temperature. Sometimes it's called a color temperature, this kind of a temperature. But because Lyman alpha photon scatters so many times in the medium, it does reach a thermal equilibrium. And in thermal equilibrium, T alpha again becomes equal to Tm. And this has very important implications for what we are going to say next. Okay. Now I include all the processes. We have discussed 3 processes during this lecture. And they are all listed here. N2 by N1 going to be determined by which of these processes is important and which of them is not. I mean, the point is whichever is not important can be neglected. So in the numerator, you can see I have put 3 processes, one corresponding to CMB, P01 gamma, which is CMB, P01C is collisions, P01 alpha, that's Lyman alpha, right? And of course, all rates of except spontaneous decays. By the way, one thing about equilibrium which one should ask, is this formula even correct? Like I told you, this formula is only correct if one of the processes generally dominates and relaxes it to a thermal equilibrium. But there are other time scales in the problem. First and foremost, we have to establish that the rate of these processes is more than the expansion rate. Otherwise, I cannot be equating these algebraic relations. I should be solving a differential equation, just like we did for determining recombination history yesterday. I mean, we can write down this differential equation and solve it. But it turns out that all of these processes that I have listed here, for all redshifts of interest to us, the rates are indeed more than the expansion rate. So we are on good term, and I'll show it to you in the next view graph that it's indeed the case. Okay, so we have all the processes. We know the rates of all the processes and the rates of all the inverse processes. So now we can ask what the hyperfine level population is at any given redshift. For that, I mean, equation 14 suffices. We don't have to do anything more than that, but we want to write everything in terms of something which makes sense from the point of view of thermodynamic equilibrium. So we define a spin temperature, which is defined in the following way. So it's defined like this. Equation 15 defines spin temperature. So I define the ratio of the two level N2 by N1 in terms of what I call spin temperature. In astronomy, again, this term spin temperature has come from the original paper of Field. Generally, it's called excitation temperature. In the rest of astrophysics, in interstellar medium, when we define temperatures like this, they're called excitation temperature. So you'll have a Tx next to it. You won't have Ts next to it. One can solve it. And once you solve this equation, so now you have h nu by kTs. So you assume that all the temperatures are much larger than the T star, which is the equivalent temperature of the hyperfine line. So you can expand all of these in first order. So for instance, the exponential can be 1 minus h nu by kTs. After that expansion, you get equation 16, and equation 16 is the master equation, which is used everywhere. I have retained T star explicitly in equation 16, but T star is generally completely neglected here because it's very, very tiny. As I told you already, T star is 0.068 Kelvin, which is very tiny compared to any other temperatures in the problem. And the other quantities, I have defined some quantity, the efficiency, you can call it, of collisions, the efficiency of Lyman alpha transition. And these relative efficiencies depend on the number density. For instance, the efficiency of collision depends on how many atoms are there to collide with other atoms. And the efficiency of Lyman alpha depends on how many Lyman alpha photons are there, right? And we already discussed it. One question I have for you before we move on, that you can easily see from equation 15 that the exponential term is extremely tiny, right? So it can be neglected actually. We retain it in the first order because we want to write this equation and want to study thermodynamic equilibrium. But still, N2 by N1 is on the order of G2 by G1. It's nearly 3 times atoms, as many atoms in the excited state as in the ground state for all times actually. Haven't you studied that if there are more number of atoms in the excited state than in the ground state, they should be a Maser's form or a laser form? Why don't they form actually? This is a question for you, so I want one of you to try to answer it. Why doesn't it happen? You can try. One of you can actually try. You can first say you understood the question. Did you understand the question asked of you? Do you appreciate the fact that N2 by N1 is indeed equal to G2 by G1 because the term under the exponent is actually extremely small, right? And I've used it actually in deriving equation 16. So why doesn't you form you have already always told this, weren't you? That you actually can form a laser when there are more number of atoms in the excited state than in the ground state. You can actually have stimulated emission, and that's what can cause masers or lasers. Why doesn't it happen?
So I can be wrong, but I will.
Go on.
I what
Absolutely.
I think this is the hyperfine level we are talking about, and it's only split in the S one S of
Correct.
only. Okay, and when we excite or form H1, it like it get excited into upper level, which is not. It's the hyper level, I think.
Yes, it's hyperfine level.
Okay, and then when we excite when we form H1, the electron jump into upper level of N. I think this N and that N is not the same here. It is just the hyperfine level. And
so you mean to
actually,
say it is not possible to have a laser in hyperfine levels? Is that what you mean?
yes. I'm not sure about that actually.
Okay, somebody else wants to try it.
Hi.
Go on.
Can I say? So I think it is due to the intermediate metastable state is not here. So that's why it is not possible to form a laser, which is required for an actual lasing thing. You need to have some metastable state in between.
Well, was a metastable state in the middle. I agree with you. That's what we were taught. But was it because of the actual practical application in laser, or was it because of the physical? Was it a requirement of physics?
It is required due to the coherence. Means if you don't have that metastable state, I think the transitions are not coherent. So the atoms get down to the metastable state, sit for some time, and then they coherently make a transition to the ground level, and then you get a coherent emission of laser. Like
coherent emission is because of the stimulated emission, right?
Yeah, but okay.
Is that what it is? Okay, all right. Fine.
For stimulated emission, we need external radiation, right?
That is correct.
Yes.
And that whether that radiation is available for this one or not, that's the question.
CMB.
CMB.
Okay.
External radiation available to you.
Okay.
So yeah, its external radiation is there, right? Somebody else wants to try it? Okay, I will try to answer it because we'll run out of time also very soon. So somebody said it is not possible in hyperfine level. That is incorrect. It is possible whenever you have 2 levels or 3 levels. It is not true. It has nothing to do with hyperfine splitting or anything. It is entirely possible for this line to maze. Second, do we need a metastable state? Actually, it's a strange thing we are talking about metastable state. You know, the A coefficient of the metastable state is actually more than 10 orders of magnitude smaller than the lifetime of this state. Actually, this state has a lifetime far larger than any metastable state we require in mazing, actually. So that is actually not correct answer. We need metastable state for lasing action because that is the metastable state does not decay so well as compared to, so what we generally need is a 3-level laser. We go to the excited state, and through an internal transition, we go to the metastable state, where the number of the population builds because it doesn't decay very well. It is metastable, right? Its transition from the metastable state to the ground state is either a magnetic dipole or it is forbidden. But even the most forbidden transition of atomic levels doesn't come close to the hyperfine level. So that explanation is correct, but it's needed for a practical reason. The answer to this is much simpler, actually. Answer to this is, to have mazing, you need level population per degeneracy state, level inversion per degeneracy state. You do not, this is not a good enough example of that. So if per degeneracy state, you actually had a level inversion, then you will form a maser. But that can never happen in thermal equilibrium. In thermal equilibrium, you can never form a maser. And I will show it to you tomorrow. that this is indeed the case. And that is the reason why I raised this point. That when you say laser, because of population inversion, you mean per degeneracy state. The degeneracy of a ground state can be 1, the degeneracy of the upper state can be 10. If you have 9 times as many atoms in the upper state, you still want maze because the inversion per degeneracy state is still less than 1. So you can pump photon and cause this line to maze. It's possible, but not in thermal equilibrium. Through pumping, it is possible. So I hope I have made my point clear, and I'll prove it to you tomorrow. And that is why I raised it today, right? So that you appreciate when you come tomorrow, you have it in your mind. Oh, we are going to discuss something about what might maze or what might laze. Okay, so I think I'm running out of time. So let me finish my lecture. All right, I do not have much time. So please read about it. Okay, these are relevant numbers that I have listed here to compute various processes we discussed during this lecture. De-excitation rate by hyperfine level by CMB. This rate I have listed here and you can compute it yourself. De-excitation rate of hyperfine level by collision. Again, I have computed this rate for typical cross sections, which I discussed, and I've listed it here. And by Lyman alpha also I have listed here. There are a few things you will notice that initially the CMB would dominate. Sorry, later, initially the TCMB and T collisions and CMB, they lead to the same outcome. The reason is because the temperatures of matter and CMB is the same. But at high enough redshift, collisions will dominate. You can actually see collisions will dominate, and because the cross section increases 7/2. The rate increases 7/2 as opposed to CMB. At a much later time, once you put in Lyman alpha into the medium, and if suppose you have the same density of Lyman alpha photons as number of baryons, then Lyman alpha dominates. And this is going to have a huge bearing on what we get to observe. And I'll discuss it in great detail tomorrow. But you would notice that all of these three processes indeed have rates which are larger than expansion rate, and I've listed the expansion rate here. Can you have self-absorption and reduced emission? I will come to this point tomorrow and not in today's class because I'm running out of time. What I'll do, I'll end today's lecture with this plot. What I have shown here are 3 temperatures. One is a solid line, and you may recall yesterday's lecture, this line is CMB. And this is temperature of CMB, and it is falling as 1/A. What is the dash? The dashed line is the matter temperature, and you notice that matter temperature is, again, decoupling. The matter temperature becomes lower than CMB temperature after a certain epoch, close to a redshift of 200. So it falls below. But there is a third curve. Third curve is the curve, it's a dot dashed curve, if you might recall. It's a dot dashed curve which merges with the other two at high redshift. This is the spin temperature. So initially the spin temperature is equal to the common temperature of CMB and matter, which is expected because matter temperature and CMB temperature are exactly the same. But later on, the spin temperature becomes closer and closer to the matter temperature because the rate of collisions dominate the process of mixing the hyperfine levels. So TS becomes closer to the matter temperature. And if you notice, after a while, it begins to deviate, which is in line with what I have written here. At low redshifts, collisions are not going to dominate because the rate of collisions falls as z to the power 7/2. And if you keep these numbers and you can note down these numbers and you can compute them yourself, of course, right? You would notice that at low redshifts, the spin temperature becomes equal to the CMB temperature again. And this will have a bearing on what we are going to do later on. So this is what happens to spin temperature. And I have not yet invoked whatever happens during the reionization era. So this is the evolution of spin temperature in the pre-reionization, pre-dawn phase, the phase in which the universe is evolving passively and first structures have not formed. Tomorrow, I'll start the lecture by telling you what happens when the first structures form. And we'll take this narrative forward. I would like you to note down these numbers. So I think I will stop now because I'm running out of time, and I'll take your questions. Please.
Hello.
Maybe
Go on.
hello. Yeah, maybe you can answer. I guess you can answer this maybe tomorrow. But I just wanted to. I was just curious to know about these collisions. So as the structures form because of the gravity, there will be more and more dense gas, right? So will
Correct.
it have any effect on the de-excitation rate of hyperfine level by collisions?
Absolutely, it will have.
Mhm.
Absolutely, it will definitely have, and I'm not going to discuss it, but
Mhm.
I'm sure in other lectures you will. But you see, many things happen when the first structures form.
Mhm.
You
Mhm.
also have heating.
Correct.
The gas heat. So typically, when the first structures form,
Mhm.
the local density increases by roughly a factor of 200.
Correct.
So that will increase the hyperfine. That will definitely increase this rate.
Mhm.
So in a formed structure,
Mhm.
you will be able to couple the gas back through collisions,
Okay. Correct.
but not in the intergalactic medium.
Okay.
So absolutely, in a formed structure, you will.
Mhm. But that will
Because
be only up to high density regions, only high
high
density.
density region, but high density region also the velocity will increase, so the temperature will increase.
Mhm.
So this factor will be slightly different, z to the
Correct.
power 7 by 2, because velocity will increase.
Mhm.
So if you form a structure, suppose like you have a structure of 10 to the power 8 solar masses,
Mhm.
it's a the virial temperature would be close to 10 to the power 4. So the increase in temperature will make a difference to collisions too.
Correct.
It'll
Correct.
increase the rate.
Mhm.
And the baryon density would increase by a factor of around a few hundred, right?
Mhm.
So
Yes.
this rate will increase.
Mhm.
Yeah,
And when you form the first structures, you will also change this lamin alpha photon coupling, right? Because then you will have more and more lamin alpha photons.
that is correct.
Mhm.
Wow, by the way, very complicated. In first
Okay.
structures, see, lamin alpha doesn't travel that far.
Okay. Mhm.
In within, oh, but within structures, yeah, it will. But the process I'm going to describe, it will travel far, so it can actually penetrate anywhere. But
Mhm.
yes, lamin alpha coupling and these collision coupling. For
Mhm.
instance, you are talking about a situation that typically happens in a neutral cloud in the interstellar medium.
Correct.
So again, we see both of them playing a role in coupling the interstellar medium gas generally to matter temperature.
Mhm.
But we do not know it for sure. If I were to answer your question honestly,
Mhm.
we do not know if the interstellar medium spin temperature is indeed the matter temperature or not.
Correct.
There is still a fair amount of uncertainty regarding that.
And this is also true for post-reionization. I mean, very
Yeah, it's
close.
true.
The
It's true of all
collision.
H1 gas. I told you interstellar medium. We can be
Mhm. Correct.
studying a
Correct.
local cloud actually.
Yes, exactly.
So when we study a local cloud, we look at, for instance, the kind of collision rates we would have had, right?
Correct. Correct. Yes.
And we try to see what
Mhm.
Lyman alpha could have penetrated in the cloud, which is hard to guess actually.
Okay. Correct. Correct.
So I could have discussed it a little more. Maybe tomorrow, if I find time, I can discuss it a little more, how exactly it is done in the interstellar medium.
Mhm. Correct.
But it is not an easy process, even in
Mhm.
the interstellar medium, to assess whether so what we try to do is, and let me come to it tomorrow when I talk about absorption and emission. If you have both emission and absorption data, you can say a little more of what the spin temperature is and
Correct.
whether it is close to matter temperature or not.
Mhm.
Remind me this again tomorrow. If I remember it, I'll come to it, or you please remind me.
Sure.
Okay.
Yeah. Yeah.
After I've written down those equations, we'll discuss it further.
Thanks.
Yeah. Please go on. Are there any further questions?
So I have one doubt, but
Go
actually
on.
it's a bit of off lecture. I had this doubt in my mind from start, like about the color temperature.
Go on.
So I studied somewhere that it is somehow related to the slope of a graph between intensity and frequency. Is it correct?
That is absolutely right.
Or can you shed more light on it?
See, the point is, all right, like let me just go here. What we do generally in astronomy, we are studying gas or its property for a very narrow range of frequencies. Okay. So it could be, for instance, we are studying a star. Okay. We are studying a star in only optical light. Star
Yes.
behaves more like a black body, but it has all kinds of other emission and absorption processes. So what I can do is I can compute the intensity at two neighboring wavelengths. I can take their ratio and define a quantity like equation 13. Okay, this is for collision rates, but I can actually easily do it for a ratio of intensity. By the way, this is a ratio of intensity in some way because P01 and P10 depend on the number density of laminar alpha photons as I've defined here, right? That allows you to compute what you call a color temperature. You do not want to use it, it's entirely up to you. But what color temperature does for us is it allows us to write neat relations like equation 16. There are many people who would say, I don't want to write anything more than equation 14. Equation 14 has physics, right? All the physics that I need is in equation 14. Do I need to write equation 16? Well, it's up to you if you don't want to write it. But the reason why we write it is because we want to study processes close to thermal equilibrium. So when the color temperature goes close to the temperature of a physical process which we know, for instance, color temperature of light in stellar atmosphere approaches the temperature of the gas. Do I want to know that or not? So that's why we define color temperatures. Or for that matter, brightness temperature. I'm going to define brightness temperature for a narrow range of frequencies tomorrow. So yes, it's up to you how you want to actually do that. What I want to emphasize is physics is in equation 14. It doesn't actually, equation 14 is based on just physical processes I've defined and I've made no assumptions. Is that point clear actually to everybody? I wanted to emphasize this. Is it clear to you that I could have done without defining T alpha, without defining Ts or any temperature so long as I had equation 14 with me? I can simply have solved it and given you numbers, right? And everybody can go home happily. They would not want me to compute equation 16. But there is a logic to equation 16, and the logic is most processes happen pretty close to equilibrium. And equation 14's rationale to in some ways is driven by the fact that there is a near equilibrium in this process, right? After all, equilibrium can only happen, right, if thermal equilibrium also holds. So that is why we define all these quantities. Color temperatures, brightness temperature, and various things which are based on ratios of intensity or, like you said, slope of a plot in a narrow range of frequencies. But you should know why we do that. And in all cases, we can do without defining such quantities. We can use equation 14 instead of equation 16. I hope I've answered your question.
Thank you. Yes.
Any further questions or I think, all right, it's almost 3:40.
Yeah, so thank you, Shiv.
Let's stop. And so tomorrow my lecture
Yes.
is at 11 o'clock, right?
Yes, yes, I hope.
Yeah, okay,
Yeah.
yeah. So we'll meet tomorrow then. Yeah.
Yeah. So thank you. And